Imagine a power source so abundant it could run civilization for millions of years. No carbon emissions, no radioactive waste, no fuel shortages. Just clean, almost infinite energy pulled from the same process that powers the sun itself. Scientists first understood this concept in the 1950s. They said fusion power was 20 years away. Then it was 20 years away again and again. For 7 decades, the joke in physics circles was that fusion is always 20 years away, and always will be. But in December 2022, something changed. For the first time in human history, a fusion reactor produced more energy than it consumed. So what took so long? Why did it take 70 years to crack what seemed like a straightforward idea? And are we actually close, or is this just another false dawn? To understand why fusion is so hard, you first need to understand why it works at all. Everything around you is made of atoms. At the center of every atom is a nucleus, a dense cluster of protons and neutrons held together by something called the strong nuclear force. It's the most powerful force in nature. Now, when you take two small nuclei, like hydrogen, and smash them together hard enough, they fuse into a new, heavier nucleus. And here's the key. That new nucleus weighs slightly less than the two original ones combined. That missing mass doesn't disappear. It converts into pure energy. This is Einstein's famous equation, E equals mc squared. And because the speed of light is enormous, even a tiny amount of missing mass releases a staggering amount of energy. The sun does this 600 million tons at a time every single second. In the 1950s, after the hydrogen bomb proved fusion could release unimaginable energy, physicists thought, why not control it? Harness it slowly, steadily, and use it to generate electricity. The idea seemed logical, almost elegant. They had no idea what they were getting into. Fusion requires one thing above all else: heat. Specifically, temperatures above 100 million degrees Celsius. That's roughly 6 times hotter than the core of the sun. At that temperature, hydrogen becomes a plasma, a superheated soup of electrons and nuclei moving so fast they can actually overcome the electromagnetic repulsion between them and fuse. Simple enough in theory. In practice, it created 3 problems that took decades to even partially solve. Problem 1. Containment. No material on Earth can physically touch a 100 million degree plasma. It would instantly vaporize anything it contacted. So how do you hold it? The answer physicists arrived at was magnetic fields. Since plasma is made of charged particles, powerful magnets can push and pull it, keeping it suspended in the center of a chamber, never touching the walls. This idea led to the tokamak, a donut-shaped reactor that uses magnetic coils to keep plasma circling in a loop. The Soviet Union built the first one in the 1950s. It seemed promising, but plasma, it turns out, is extraordinarily unstable. It writhes, it kinks, it develops instabilities with names like kink mode, sausage instability, and ballooning mode. Every time physicists thought they had it contained, the plasma would find a new way to escape. Problem 2. Heating. Getting plasma to 100 million degrees is not like turning up a thermostat. You need to inject enormous amounts of energy through microwaves, neutral particle beams, or by running massive electrical currents through the plasma itself. But the more energy you inject, the harder it becomes to contain. The plasma gets more turbulent, more unstable. It's like trying to hold water in your hands. The harder you squeeze, the more it slips through. Problem 3. Energy balance. This is the brutal one. To make fusion useful, you need to get more energy out than you put in. For 70 years, every single fusion experiment consumed far more energy than it produced. Scientists called this ratio Q. A Q of 1 means you break even. For decades, the best machines barely reached Q of 0.6 or 0.7. The plasma would heat up, start fusing, then cool down or escape before it could sustain itself. It was like trying to start a fire with wet wood. You keep applying heat, but it never quite catches. Between the 1960s and 2000s, fusion research consumed billions of dollars and produced no usable electricity. Governments grew frustrated. Funding was cut. Brilliant scientists spent entire careers on machines that never quite worked. But this period wasn't wasted. Every failure taught something. In the 1970s, physicists discovered that adding a second type of hydrogen, deuterium and tritium together, made fusion far easier. The reaction happened at lower temperatures, with less energy input. In the 1980s, computer modeling finally became powerful enough to simulate plasma behavior. Scientists began to understand why plasma went unstable and how to prevent it. In the 1990s, the tokamak design improved dramatically. A machine called JET in the UK achieved a Q of 0.67 in 1997, still not break-even, but closer than anyone had come before. And in 2006, 35 nations agreed to build the largest fusion experiment in history, ITER in southern France, a machine so big it would finally, definitively prove whether fusion could work at scale. ITER was supposed to be finished by 2016, then 2020, then 2025. It's still not complete. Fusion, as always, was 20 years away. But while governments argued over ITER's budget, something unexpected happened. Private companies entered the race. In 2022, a facility called the National Ignition Facility in California, not a tokamak, but a laser-based fusion machine, fired 192 lasers simultaneously at a tiny pellet of hydrogen fuel the size of a peppercorn. The lasers delivered 2.05 megajoules of energy. The fusion reaction produced 3.15 megajoules. For the first time in history, a fusion reaction had achieved ignition, producing more energy than it received, Q greater than 1. The room reportedly went silent, then erupted. It wasn't enough to power a city. The lasers themselves required far more electricity from the grid than the reaction produced. But as a proof of concept, it was historic. The fundamental physics worked. The barrier had been crossed. Since then, progress has accelerated. Commonwealth Fusion Systems, a startup spun out of MIT, is building a compact tokamak using new high-temperature superconducting magnets that are dramatically more powerful than anything before. They aim to demonstrate net energy gain by 2025 and build a commercial reactor by 2030. Other startups, Helion, TAE Technologies, General Fusion, are each pursuing different approaches, backed by billions in private investment. So why did it take 70 years? Because fusion sits at the intersection of the hardest problems in physics and engineering. Plasma physics, material science, superconducting magnets, computer modeling, cryogenics, every single one of these fields had to advance before fusion could work. It wasn't that scientists were failing. It's that they were solving problems that had never been solved before, in sequence, one by one, over generations. The 20 years away joke might finally be outdated, not because the optimists were right all along, but because 70 years of patient, incremental progress quietly built the foundation that the final breakthrough needed. The sun has been doing this for 4.6 billion years. We figured it out in 70. That's not a failure story. That's actually pretty remarkable.